Today, we will see in detail the partial wave analysis part 1. I have divided this lecture in two parts. Today, we are going to see the part 1. So far, we have seen only the approximate method to solve the scattering problem, like Born approximation, where the interaction between the projectile particle and the scattering potential uh, V of R is small compared with the energy of the incident particle. So the comparing the energy of the incident particle, the interaction between the particle and the scattering potential is small. With that approximation, we have solved the scattering problem. Today, we will see without imposing such a condition how to solve the scattering problem using partial wave analysis. This method used to calculate the scattering cross section without placing any limitation on the strength of the potential V of R. It is a technique for solving scattering problem by decomposing the each wave into its constituent angular momentum component. That is, we are collecting the wave which are having same angular momentum, and we are solving it using the boundary condition. So here there is no limitation in the strength of the potential. The scattering problem can be explained using this simple diagram. I have not drawn to the scale. The inner circle, in fact, in three dimensions spherical shape. So inner sphere where you have non-zero potential, which I have shown in the yellow shadow. This region you have non-zero potential, and outer circle you have that is called the intermediate region where the potential is zero. Away from this, you have the radiation zone in which the K into R is very much greater than 1. Since this is the small sphere, this is a scattering region which is a small sphere. Then the potential to be spherically symmetry as it is a very small sphere. Uh, the angular momentum of the incident particle in the scattering region will therefore be conserved. The angular momentum of the incident particle will be conserved. A particle scattering from the central potential will have same angular momentum before and after the collision. The most general solution of the Schrodinger wave equation is particularly in spherical polar coordinate e power ikr. This is the Schrodinger plane wave equation e power ikr. In Cartesian coordinate, it is e power ikr. In spherical polar coordinate, it is equal to summation over LM CLM RKL, which capital RKL, which is a function of R alone, and YLM, which is a function of theta and pi. This is the angular part of the wave function. This one is the radial part of the wave function, and CLM is the expansion coefficient. We know that the radial equation is this one. And I have explained in detail about the radial equation in my lecture on radial equation. You can refer my earlier lecture on radial equation. I think I need not repeat that here. Uh, so at a very large distance, the potential goes to zero. You can see from this diagram. I have divided it into three portions. One is the yellow shaded one is the scattering region, and the outer circle is intermediate region, and uh, the above the outer circle, it is the radiation zone where K k into r is very much greater than 1. So at very large R, the potential goes to zero and the centrifugal contribution is negligible. Here the second term is the centrifugal contribution and the third one is the potential term. So both the second and third term will cancel out because second one is negligible, third one is zero. So this equation will become T2U over TR2, which is approximately equal to minus k squared U. The general solution for this one is U of R is equal to A e power ikr plus b e power minus ikr. So the solution for outer region, that is region 3, is u of r a e power ikr plus b e power minus ikr. Here, this first term represents the outgoing spherical wave, and second one is the incoming one. For scattered wave, we evidently want P to be zero, this to be zero, because we are dealing only with the outgoing wave. At very large R, that is E of R will become, because at very large R, we are assumed that it is zero. It is zero because at R is infinite, this term will get cancelled. So U of R, which is equal to R into capital R of R. The reason for replacing R by U of R, I have explained in my previous lecture on radial equation. So you can refer that one, which is approximately equal to e power ikr. Here I have taken a as 1. Hence, the radial part of the wave function will become r of r is approximately equal to e power ikr over r. Just now, we have seen the solution outside the outer circle, that is in the radiation zone where K into R is very much greater than 1. Now we will see the solution at the intermediate range and at the boundary more specifically. So uh, let us say this your wave is traveling along z direction. So the plane wave equation is E I K Z, and this is this solid circle is the scatterer. So uh, this is the scattering act as a scattering center. At the intermediate stage, at the as well as at the boundary, this equation will become the third term will become zero because potential is zero at the intermediate stage. So this will become zero. So the Schrodinger wave equation will become T2U over TR2 minus L into L plus 1 over R squared U, which is equal to EU. Uh, so here, since this potential is localized, this equation you can notice that I like to notice that important point. It is independent of the potential. We are not worried about the strength of the potential. Only thing is we have taken this is localized one. The general solution for this type of equation is a linear combination of spherical Bessel function. That is u of r is equal to a r jl, which is a function of kr plus p into r nl, which is a function of kr. Here, JL is the Bessel function of first kind, NL is the Bessel function of second kind. JL is represented as a sine function, NL is represented as a cosine function. Uh, for our current example, neither JL nor NL represents an outgoing or incoming wave. Actually, we need a wave in the form of linear combination of e power ikr and e power minus ikr, which are known as spherical Hankel function. That is, linear combination of these two function is called spherical Hankel function. We will see now. There are two type of spherical Hankel function. Hutchel1, which represents the Hankel function of kind 1, is equal to JL of x plus INL of x. Similarly, the Bessel function of kind 2, represented as HL2, which is a function of x, is equal to JLX minus INLX. Uh, Here, if we take the asymptotic behavior, you know very well what is asymptotic behavior. For asymptotic behavior, we need that k into r must be very much greater than 1. So in this case, the spherical Hankel function of kind 1 is equal to is represented by this equation, that is minus I power L plus 1 e power ikr divided by kr, which represents the outgoing wave. Similarly, the Henkel function of type 2 is represented by I power L plus 1 e power minus ikr over kr, which represents the incoming wave. So now we are particular about the outgoing wave, that is the Henkel function of first kind. At large R, uh, Henkel function of kind 1, that is Hutchel1 of Kr, goes like e power ikr over Kr, whereas the Henkel function of kind 2 goes like e power minus ikr over Kr. So for outgoing wave, then we need a spherical Hankel function of first kind. That is this one. This represents the outgoing wave. So naturally, the radial part of the wave function is equal to approximately equal to Hl1 kr. Thus, the exact wave function outside the scattering region where Vr is equal to 0, V of r is equal to 0, is psi of r theta pi, which is equal to a into e power ikz plus summation over lm clm h l1 of kr ylm, which is a function of theta and pi. We have seen already this one, except here the I have shown in green color band, which is equal to RL. I have replaced R of L by this one, HL of 1. That is, I have replaced the radial wave function in terms of Hankel function. So here the first term represents the incident plane wave. Second term represents the scattered wave. Here, as usual, CLM is the expansion coefficient. This HL we have replaced for the radial part of the wave equation. Uh, since we assumed that this potential is spherically symmetric, because as potential is localized, the wave function cannot depend on pi. So that means m must be equal to 0. And we know very well that YL0, which is a function of theta alone, because pi dependence goes away, because it is spherically symmetry, which is equal to square root of 2L plus 1 divided by 4 pi into PL cos theta. So here now I have replaced this YL 0 Since m is equal to 0, the summation become only L, summation over L. I have replaced this YLM, YL0 pi square root of 2L plus 1 divided by 4 pi PL cos theta. Finally, the total wave function, which is a function of r and theta, will become like this. Here, it is customary to redefine the expansion coefficient CL0 because we have taken m is equal to 0, which is equal to I power L plus 1 k into square root of 4 pi 2L plus 1 AL, where AL is called Lth partial wave amplitude. Since waves with the different values of the orbital angular momentum are referred to as partial wave. So this is the key parameter why we are calling this as a partial wave analysis. So just you substitute, you replace CL0 by this term, that is K I have taken out of the summation. K summation over L, IL plus 1 square root of 4 pi 2L plus 1 AL, and this Hankel function, and this term square root of 2L plus 1 divided by 4 pi PL cos theta. Finally, we arrived with this expression. Uh, if you see the expression carefully, we can simplify this expression, that is summation over L. Here you have square root of 4 pi, here in the denominator you have square root of 4 pi, which will get cancelled. And I have shown in the yellow highlight, that is square root of 2L plus 1, here also square root of 2L plus 1, which will become 2L plus 1. This is the 2L plus 1, and this term I have taken as it is, that is I power L plus 1, I have taken I power L plus 1. And of course, this one is a HL1, which is a function of KR, and this PL cos theta I have taken as it is. Already there is a 1K. Uh, and just 2 minutes back, we have seen that for a very large R, the Hankel function goes like minus I power L plus 1 into e power I kr divided by kr. So you replace this Hankel function by minus I power L plus 1 e power I kr over kr pl cos theta. That is just I have replaced the Hankel function by this one. Finally, we arrived with this expression. I want to simplify this expression further. You see here 1k in the numerator outside the summation, and here 1k in the denominator, which I have shown by yellow highlight. So both will get cancelled. Similarly, I power, if you multiply the I power L plus 1 into minus I power L plus 1, that is I have shown in green color shading. This will become, if you multiply these two, this will become 1 for all value of L. That is more important. For all value of L, this will become naturally 1. So this K also get cancelled. So you will get the remaining term 2L plus 1 AL PL cos theta e power IKR over R. So we have already found that the total wave function for the scattered wave is equal to e power a into e power ikz. This is the incident plane wave, and this is the outgoing scattered wave, that is which is equal to f of theta e power ikr over r. If we compare these two equations, then e power ikr I have shown in the red color bond. So remaining term will be that is f of theta. So f of theta is nothing but uh, this term, that is 2L plus 1 into AL PL cos theta. So this is the f of theta. By comparing both, you will get f of theta is equal to this one. So this is equal to f of theta. That's what I have written here. F of theta is equal to 2L summation over L 2L plus 1 AL into PL cos theta. We know that the differential scattering cross section T sigma over T omega is equal to modulus f theta squared, f of theta squared. Here f of theta is a scattering amplitude. So this can be written as f of theta into f star of theta. F of theta I have mentioned in the red color band here, 2L plus 1 AL PL cos theta. And f star theta is shown in the black color band, that is 2L prime plus 1 star, that is complex number, AL prime star, and PL prime cos theta. After integrating the differential cross section and using the orthonormality condition for Legendre polynomial, that is this two term, that is integral PL of x into PL prime of x dx is equal to 2 over 2L plus 1 delta L L prime. Here this is the Kronecker delta. This is one only when L is equal to L prime. So the summation over L and summation over L prime will become just summation over L. And here, since L is a real number, so 2L plus 1 into 2L plus 1 complex will become 2L plus 1 squared in the numerator. In the denominator, you have here 2L plus 1, which will get cancelled. Simply, you will get 2L plus 1. Similarly, if you multiply this, you will get AL modulus AL whole square. Uh, and this, if you integrate over the solid angle, you will get 4 pi. This will become sigma is equal to 4 pi into summation over L into 2L plus 1 AL square, where modulus AL square, where AL is the partial amplitude of the Lth wave. So this is the total scattering cross section. Here you remember that we have taken only the scattering part of the wave function. We have not taken the incident wave. But the actually the scattered wave consists of both incident wave and as well as the scattered wave. We will see in the next lecture what will happen if you take the instant wave also. Uh, we will see the more detail in my lecture, in my next lecture, that is partial wave analysis part 2. Thank you very much for watching my video and supporting me continuously. Thank you.